Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this video I will discuss how to optimize a univariate function. Managerial economics is all about decision making. This can be decision making by firms, governments, or individual people. We are going to approach decision making as optimization problems. When optimizing, decision makers might have different priorities. Individual people might be trying to maximize their utility, whereas firms are usually going to be maximizing profit. Optimization can also be about minimizing. A factory manager might want to minimize costs to produce a certain amount of output. Whatever kind of optimization problem we're doing, the economic agent has control of certain things, which we call choice variables. The goal of any optimization problem is to find values for the choice variables that will lead to an optimal outcome. The relationship between the choice variables and the outcome of interest is called the objective function. The objective function gives a mathematical relationship between the two. For example, a firm's objective function might be their profit, and their choice variables might be the price they set and the amount of advertising that they do. Objective functions can have many choice variables, but for right now we're going to stick with a univariate objective function that just has one choice variable. In most of the problems that we explore in this course, we are going to look at continuous choice spaces as opposed to discrete choice spaces. In a discrete choice space, there are a set number of options available, and it's relatively simple to optimize those kinds of functions because we can just check the values for our different options and see which one is the best. In a continuous choice space, we have an infinite number of possibilities. As such, we're going to need to use derivatives to optimize the function. From here, I'm going to assume that you have the basic derivative rules down. If not, please review the previous video. For now, let's suppose that we have a choice variable x and an objective function f of x. F of x is the mathematical relationship between x and the outcome of interest. Suppose our goal is to maximize f of x. I will use Leibniz notation to denote the derivative of our objective function, df dx. If the derivative is positive, this means that our function is increasing as the value of x increases. If we're trying to find the value of x that maximizes f of x, this means that we can increase x and do better, and so x is too low. On the other hand, if df dx is negative, that means f of x is decreasing as x increases, meaning that we can do better by decreasing x, or x is too high. This means that the optimal value of f of x must be where the derivative df dx equals 0. This equation is called the first order condition. Usually abbreviated as FOC. Setting up the FOC is the first step of any optimization problem. Let's look at an example. Suppose we have an objective function f of x equals negative x squared plus 10x plus 5. If I take the derivative of this, we get df dx equals negative 2x plus 10. Derivative of 5 is 0, so that just drops out. What I've just written is the first derivative. To get the first order condition, we set that derivative equal to 0. From here, we need to solve the first order condition to find the value of x we're looking for. I'll add 2x to both sides, and then divide both sides by 2 to get x equals 5. This tells us that at a value of 5, we have found the maximum value of f of x. But we're not quite done. The point we found could be a maximum, but it could also be a minimum. To figure out which one, we need to use the second derivative. The second derivative is the derivative of the first derivative. We denote that with d2f dx2. We just take the derivative of the first derivative, which is right there. The derivative of negative 2x is just negative 2, and the derivative of 10 is 0. In our example, the second derivative is a constant number, -2, but it doesn't have to be. It can also be a function in certain other cases. What we're looking for here is the sign of the second derivative. In our case, it is negative. When the second derivative is negative, then we have a maximum. And if the second derivative is positive, then we have a minimum. To think about this graphically, the second derivative being negative means that the function is concave. That is, it looks something like this. Looking at this graph, to the left of the dotted line, the derivative of this function is positive, meaning that it is increasing as x increases. To the right of the dotted line, we have the derivative negative, meaning that it is decreasing, and at this point right here, that is where our first order condition is satisfied. When the second derivative is negative, that means that parabola, in our case, is facing down, and so we found the top. When the second derivative is positive, the function has a shape like this, where that point where the first order condition is satisfied, the derivative is 0, we have the minimum as opposed to the maximum. To finish this up, let's figure out what the maximum value of our example objective function is. Recall that our objective function is f of x equals -x squared plus 10x plus 5, and we figured out the maximizing value of x is 5. So we're going to plug that in to get f of 5 equals -5 squared plus 10 times 5 plus 5. That gives us -25 plus 50 plus 5, which comes out to 30. That is the basic idea of how to maximize a univariate objective function. This is the simplest kind of optimization problem, but one that we will do many times throughout this course. In the next video, I will introduce the methods we will use to optimize multivariate objective functions.